Okay, so welcome back to the channel. So today we're going to cover mesh analysis, and so I put here an image of a robot, really my mesh robot. And the question I had when I first started looking at mesh circuits way back when is really what direction should I be going? Should I be going clockwise, counterclockwise? And the direction that I'm referring to is actually the direction of the current. So when it comes to the direction of the current, that used to be my Achilles heel when I was trying to work on these problems. So I have here an actual problem itself, and this problem here, as I mentioned in the previous video, is an example of a problem that takes into account two nodes. You have here a top node, and you also have here a ground node. So I'm going to highlight here with my marker. So here's our top node, here's our reference node or our ground node. And in this circuit, we have three branches illustrated by 1, 2, and 3. And within these three branches, you also have two different voltage sources. And again, I showed my examples of voltage sources in the previous video. In addition to that, we have three resistors of 1 ohm, 6, and 2 ohm, and all in parallel. A circuit like this, you can't automatically reduce it and call it a parallel circuit. And combine the resistors because you have voltage sources that are there. In other words, this is going to create a voltage drop across two of these resistors. So interestingly enough, when it comes to circuits, anytime you reach this challenge or a problem that you quite can't solve automatically at first glance, there's always a new theorem for it or a new analysis technique. And this analysis technique is called mesh. And hopefully you're going to find it to be interesting, fast, and efficient. So when we look at mesh is actually, thankfully, has a few rules that are associated with it. So there's about 5 rules that I like to keep in mind when I'm solving any type of mesh circuit. The first one, again, is to try to set your current direction. Okay, so current has a flow. I mentioned in a prior video that generally speaking, the current leaves from the positive end of your voltage source. And that's through convention for most of your circuits classes. In addition to that, so step number 2, you got to identify the loops and give a name to the mesh currents. I'm going to talk about mesh currents and how are we going to identify it next. Finally, we're going to talk about KVLs, aka Kirchoff's voltage law. We're going to write a specific equation that satisfies each mesh using a KVL equation. Step 4, we're going to try to figure out what is an actual constraint or a constraint equation, and we're going to look for that and hopefully identify it. We'll be more specific as we go on with this example. And the last step of our 5-step process is going to use a technique. Either we're going to use substitution method or a matrix form to solve the actual problem itself, because that's what mesh does. It actually lends itself to hopefully a problem that's straightforward sub or matrix form. So let's put that to the test. So here's our problem. And again, when we're looking at the problem, our very first step asks us to identify the loops and give a name to the mesh current. So again, what we have here is that we have a 2-loop problem. So I'm going to identify my loops. So here I'm drawing a circle, or at least a partial circle. Try that again. All right. We have another one over here. So far I didn't put a direction of the current. We're just going to put down either that it's going clockwise or counterclockwise yet. But traditionally, as I mentioned before, is that if it leaves the positive end, we generally expect that the current in this first loop on the left will be going clockwise. And again, because this is the positive end, negative side, positive side, negative side of our voltage source, we could also assume that it's going to go clockwise here as well. Why again? Because the current generally leaves the positive side. So we're going to expect a notation like this. Okay. Same over here. It's positive. We're going to expect it to go clockwise. So we could overanalyze this, which is the interesting part about mesh. But what I'm going to hopefully do is try to make your life easy. I will try to always, I don't like to use that word, but I like to always go clockwise direction. And I'm going to use always, well, let's say 95% of the time go clockwise. So what we also will learn, or at least from the previous video, I mentioned that when it comes to polarities of resistors do not have poles in general. So if you left a resistor in a table, they're just passive devices. So you actually have to give them their own sign convention. So if it leaves the positive end, you expect that this will be positive and negative. And again, when it comes to this resistor, the 6 ohm resistor, you also expect it to be positive and negative. And you can take a look at the previous video that I showed how to do this. And so that's number one. So that's how we're going to identify the direction or the flow of our current. Now we have to label our current as well. So I'm going to give it a name. I'm going to call this IA for the left-hand loop. And then we're going to call here IB for our right side loop. So to backtrack a little bit, mesh comes from the idea, if you can think of your screened-in porch or screen, the mesh itself looks like this, right? If you look at screened-in porch, you magnify it a little bit, it's going to have these patterns in there. Hence the name of this mesh analysis. And what we're trying to do again is that we're trying to evaluate, say that you have this screen or this mesh, how could we actually solve for the currents and voltages across each of these branches of our circuit while we analyze them? Okay, so again, so this is the name mesh comes from literally a screen design. So I'll delete this for now to not keep my screen so busy. But when we have that, the mesh itself is nothing else but that arrangement. And what we'll hopefully find out is that doing a mesh that has two loops in there, it's not terribly hard to do by hand. If you do a mesh that has 3 loops in there, it's not terribly hard to do by hand. But once you get to 4, 5, 6, let me actually put this image back so you can see a little more clearly. But if I had 1 loop here, I'm trying to identify it, it's not so bad. 2, I can do that as well. 3, right, you can also do that as well. 3 loops, it's not too hard to do by hand. But eventually, once you surpass 3, it makes more sense to use a computer and use something like MATLAB or Matrix Lab or any type of software that'll actually help you solve these problems much faster. Because at that point it becomes math than it does electrical or engineering related problem. Okay, all right, so now that we have that, I'm going to also identify positive, negative as well for this 2 ohm source as we go about it clockwise. So again, when we're looking at IA takes the form of that convention. Interestingly enough, the IB, when IB goes around this loop, what it actually sees these positive and negative on that end. Okay, so this is the positive side here, the negative side here. So let's try to figure out what's going on. So again, first we're just trying to set this up, and then we're going to take it a little bit deeper. So let's go ahead and look at this one more time. So we selected the current direction. We're going to identify going clockwise to be our most logical method for now. We're going to give it a name. We called it IA and IB. And then the third step says we're going to try to write a KVL equation for each mesh. Okay. And if you've forgotten what KVL is, Kirchoff's voltage law, the idea behind it is that for Kirchoff's voltage law, so we write it out for you, that the sum of KVL equals to 0, which is just a fancy way of saying that if I sum up all of my voltages, which means that I have 2 different things going on. I have a voltage source, right? That's contributing that energy. And I have, for example, the resistors in my circuit that are consuming some of that energy. And that net conservation, right, mathematically equates to be 0. So which is a very powerful tool and helps us solve many of these problems. And again, I went over this in a previous video. You should check that out. So if I was to write KVL's equation here, so let me also add one more thing here for clarity here. We just do one more thing just to see if that helps you. And so we have 3 branches, right? We have the outer branch, and that outer branch here, right? is essentially where I'm highlighting with this marker. And we have another branch here, right, which I'm highlighting with this marker. And we have a third branch that exists in the center. So I'm going to give that one also a name. Okay, so I'm going to call this one here, say IC. Okay, so let's try to understand what's going on. And this is how I recommend we approach this. So the first thing that we do, we write, I'm going to write our mesh equation for loop A, right? That's the left-hand loop. Okay, as I mentioned in the previous video as well, so I like to identify my corners because it helps me visualize what I'm up to. So each one of these corners here represents our left-hand loop. So if we're gonna, what I like to start with our loops, I'll also give us subnames so you can understand what I'm talking about. So I'm gonna call it I1, I2, I3, and I4 here. So you can have an idea what I'm talking about out loud. You can actually keep up with what I'm trying to say. So I'm going to always start at the bottom leftmost corner. It makes my life easy because I have a starting point always. And if I'm going to do that, that's referenced here by this position here, 1. Okay. And if I write my equations using that note, that starting point, what I'm reading here is a sign convention of each of the poles that I see first. So at the 5 volts, I see the minus, I see a positive, I see a positive, then I see a positive. Say it one more time. So if I start here at this corner A, I'm only reading not both sides of my poles. I'm only reading the side that I'm entering. So it'd be a negative, right? Positive, positive, and then positive again. And what KVL, our objective is to write a KVL equation for each one, which means I know the solution to my problem. My problem is going to net equals to 0. So the KVL for loop number on the left loop, aka my loop A, means that I'm trying to write down the voltage. KVL starts with Kirchoff's voltage law. And I'm summing up all the voltages. So the first voltage that I see is minus 5 volts. So then I'm going to add it, right, to my second voltage. Well, my second voltage is the next component that I see. And the next component that I see is the 1 ohm resistor. So in order to get a voltage source, I have to take that 1 ohm, and then I have to take that 1 ohm, and then I have to multiply that 1 ohm by IA. Okay, so a resistor times it by a current. So this is my R times it by I. This is actually the same thing as me writing down a voltage of resistor 1 ohm. Okay, see what I did there? And then the next one, I'm entering here into the positive side of the 6 ohms. So what I actually see here is I see plus 6 times it by IC. Okay. And then finally, I'm going to have here plus 10 volts. All of that equals to 0. Okay, so that's my first equation that I just wrote. And again, for clarity, the 6 times it by IC is the same thing as me writing B of the 6 ohms, right? So that's the idea behind this. So far I have one equation, and within that one equation I have 2 unknowns. I have unknown IA, I have an unknown IC. So if I was to now, let me copy and paste this so you can see it along as I go through this. I also have here, first we copy and try to paste this here for you. I also have the second loop, right? And the second loop is also going to be the same approach. So let me just copy and paste to save some time and energy. So here it is. So I'm going to copy that. And I'm going to call this, of course, loop B. And for loop B, I'm essentially doing the same thing. It's interesting copy and paste. Not everything actually copied. Or did I not copy the right thing? Let's try this one more time. So this time what we're going to do, let me try to copy this actual image. Copy. This time this should work. Okay, so as we can see here, if I was to evaluate loop number 2, our goal is now to write Kirchoff's voltage equation for that secondary loop. So where do I start again? Well, because I am completed loop 1, I am now only working on the second loop. So the second loop, it makes sense to start at the far left hand corner where I'm identifying with this green marker again. And I'll go from here and I'll go clockwise around this entire branch until I return back to the starting point. So when I write that, I'm writing down the sign convention I see first. I see minus, positive, positive. So to write that out, I'm going to be left with minus 10 volts. Then I have plus 6. Then IC again. Put this one here. And then I'm going to have here plus 2IB because I'm in loop number 2. I'm not in loop A anymore. Sorry, I'm in loop B, not loop A anymore. And all of that nets equals to 0. Okay. So again, say this for, hopefully you're getting this, but in the first loop, IA exists along this, by the way, it's an arbitrary name. It exists only through this 1 ohm resistor. IB only exists through this 2 ohm resistor, right? The 6 ohm resistor is very interesting. That is the one resistor that's sharing current between IA and IB. So how can that be? So let's try to understand it a little bit more clearly. So I'm going to draw for you the 6 ohm resistor that exists in the center. So the 6 ohm resistor, what it appears like to the 6 ohms, is that it's going to appear that IA is traveling like this. It's going to appear to it that IB is traveling like this. So in other words, the current of IA and IB are opposing directions from each other. They're going against each other. So if IA is going clockwise, it's going to appear to IB that IB is going counter that direction, right? They're going against each other. Is that concern? So there's an issue. And again, this here is really important because this here shows us something interesting. It's really part of our constraint. Right? So how do we tackle this? Okay, so there's an easy way and a hard way. So let's talk about the hard way first. Hopefully the hard way is more logical to us, and I'll reinforce something later. So let's try to understand what's going on. All right, so here it is. So if I take this circuit and I expand on it over here, and I now try to understand this visual of a constraint. Here it is. And I start to look at it from the standpoint of a node. Okay, so I have 2 nodes in this problem. The first node that I have is this top line over here. The second node that I have here is this bottom node here. And I showed in a prior video that hopefully you could identify relatively easy. But the idea is that when it comes to the nodes, the node, if I redraw it quickly, you'll see that it's going to represent this. It's going to be like this for you. Right, and this is the modified drawings that I like to do to help visualize these problems, because sometimes the visualization is the hardest part, and once you get past that, it's actually not so bad. So here's a modified same problem, but I drew it out differently. So you can see the node on top, and again, a node is a junction, a connection point where everything connects. And now here's my other node, but it gives another name. They call it the ground or a reference node as well. So there's 2 nodes technically with this problem. Okay, and here I'm illustrating that top and that bottom here, hopefully to help us define something. And what I care about is that top node. So when I look at that top node and I look at it and I try to solve for it, in that top node, what we can now do here, we can draw this node and isolate it a little more clearly. So here's how the top node looks like. And on the top node, there's two things we know 100% sure, right? The first one that we know for certain is that because we said that we're going clockwise, I can now draw the arrows for IA, right? And I can now draw, so I'm going to label it for you, IA, and I can also draw the arrow for IB, okay? So that hopefully makes sense. And how do I know that? Wait, because I determined that I'm going to go clockwise. See this here? It's going clockwise for I and AB. So the clockwise means that the current IA is going in this direction. So let me start all over again. So it goes up IA, over, and enters this node. IB, right? See how it's going clockwise? It is leaving this node. Okay, so it's leaving that node, which is really important to us. So now that we have that drawing, I see here, we're going to have it going in this direction, right? Again, hopefully this makes sense. And if we try not to overthink it so far, but the goal again is that we're going to recognize that because the direction of it, we can make the assumption that IA is going to go that way. We can make the assumption that IB is also going to be going towards the right, and then IC is going to be going down. Okay, so as you can see here, we have one node, and within that node we have a couple things going on. So we can think about it this way. You could think about the currents, the mesh currents to be more precise, as either entering or leaving the node. Okay, and why is that so important? Because when they do that, right, we could actually solve for the KCL, the Kirchoff's current law, or the current behavior at each node. So in other words, if we did the sums of the currents going in, and we also looked at the sums of the currents going out, we could come up with something kind of clever. So what's going in to this node? IA is entering this node, and IB and IC are leaving those nodes. All right, so if I wrote it out, I'll have IA on this side, and on the outs, I'll have IC plus IB. Okay, so that is how it looks like for those ins and our outs. So what does that mean from a mathematical standpoint? It means that IA equals IC plus IB. And if I wanted to know what IC really is, well, I can solve for it algebraically, and I would see that IC equals to IA minus IB. Okay, so that's number one when we're looking at this. Let me zoom out a little bit so you can see all of my entire screen, that they will actually equal each other. IC equals to IA minus IB. Okay, and that's based on the flow of the charge, right? We're just going around, we're going to go clockwise. This is what we're observing through it. And again, the current enters the positive side of a passive device. So here's the positive side of my charge, then it goes through the positive terminal, enters, and over here it enters the positive terminal. Hence why the direction here would be up. The direction across this 6 ohm on the left loop will be down. Please see if you can follow that. That's actually pretty important. Maybe not as much right now because I'll show you the easier way, but later on this will save you a lot of grief when you're looking at this. Okay, so now when we evaluate, and this is for the left loop, so let me make sure I'm clear about this. This is if we're evaluating, right? This is for loop A. Okay, this is really important. And how do I know it's for loop A and loop A exclusively? Because again, I'm entering the positive side, right? So it means I'm going clockwise. I'm entering the positive side here, going down, which means I'm also continuing my clockwise behavior. if we repeat this process, so let me copy and paste some of this, and hopefully I can do this neatly. Let's try this, see if this works. Let's see if what I'm going to do, copy and paste, and I'm going to delete some stuff and hopefully get this nice and neat. You know what? I'm going to remove a lot to make it a little more clear to you, and delete all the stuff that I don't need. Okay, now we're good. So now that I deleted most of that, I'm just repeating this. Now I'm just going to add the variables before. So now we're looking at loop B. So loop B is the right hand side. So how can we possibly enter the positive terminal? Remember, that's our goal. It's enter the positive terminal. Well, the only way to enter the positive terminal of this resistor here, right, is if we're going clockwise, we're entering that positive, and then we go down here, then we come back over to minus 10 volts, and we're going up and we're entering this positive terminal here, which is very important. Only way we can do that is if we evaluate the bottom node or the ground node. See if we can follow along this time. So check this out. I'm going to add the resistor here just to make it a little more clear. So I'm going to sketch this idea so you can get it. So IB is on the bottom. We know 100% is going towards into the node. And then this one will definitely be going to the left as well. This is IA. And this time, the only way to go into the positive terminal of the 6 ohms, right? We're evaluating loop B. This positive negative only affects the left loop. The positive negative on this side only affects the right loop. Then the only way to do that means that the arrow for IC in loop B's perspective is going to have to be up. So check that out. It's pretty powerful, actually. So that means that when I'm doing the ins, the only thing that's entering my node is IB. And what is leaving my node is IA and IC. Okay, so check out what I did. Really important that you can visualize that. And if not for this lesson, it'll be very important for the next couple of lessons. So if I were to write this, that means algebraically this will be the same as IB equals to IA plus IC. And if I solve for IC in right loop, right, I'm going to be specific so I don't confuse myself later. It's going to be IC equals to IB minus IA. Really important, right? So check that out. So because of that behavior, we finally defined what IC is, and IC is different depending on which loop we are observing our equations from. All right, and that is the hard part of doing this. There's an easier way to think about it, I hope, and we're going to try that out as well. But first, let's try to finish this problem all the way out based on what we have so far. Okay, so based on what we have so far, we have two equations, right? We have our loop 1 equation and our loop 2 equations, and I have our constraint equations that go along with it. So we copy that. I'm going to finally put everything together for you. That's loop B. And let me also put loop A here for you as well. And here's my loop A equation for you. I'm going to copy and paste that and bring it down. In fact, let me switch their spots because why? Because I prefer it to be organized. That's just how I am. All right, so move this up so you can see all of it. All right, fantastic. All right, so now that we have hopefully a better grasp of this, so now I'm going to copy my constraint equations, right? Copy that. This is for loop B. I'm going to place my constraint equation here. I'm going to put here loop B so I don't forget. And then I'm going to also put my constraint equation for loop A. I'm going to put that over here. Okay. So now the idea is that we have to simplify this problem and solve. All right, so let's try to do that now. And what we're going to do again, we're just going to substitute in any place we have, because again, right now we have two equations. Let me make sure I'm saying this clearly. We have two equations, our loop A equation, which has an IA unknown and IC unknown, and we have our loop B equation, which has an IB and an IC unknown. As it stands right now, I would have two equations and three unknowns, and that's not fun from a math standpoint. It makes more sense that we can have two equations and two unknowns. That's the universe that we normally feel comfortable with, or three equations or three unknowns, etc., etc., etc. Okay, so let's try to figure this out. So at this point, what we're going to do, we're going to try to solve for this, solve for KVL. So we have the minus 5 volts on the left hand side. I'm going to move that to the right hand side. So I'm going to have the 1 ohm. I'm going to multiply that by the I sub A, right? Plus 6, and wherever I have the IC, I'm going to put here IA minus IB. Then I'm going to have here, I had a minus 5 volts and a positive 10 volts. So I can treat that as positive 5 volts. I move it to the right hand side. It should give me back minus 5 volts, right? So now I have here hopefully abbreviated problem. So I'm going to distribute this out to simplify it a little bit more, right? Might as well. So we have a 6IA and a 1 IA, so it's going to make a 7IA minus 6 IB equals to minus 5 volts. And I finally have an equation that satisfies my first loop. Okay. And then now we're going to repeat that again for the second loop equation. So I'm going to back this out. So now I'm going to have the 6 here. And wherever I have the IC, I'm going to replace it with IB minus IA plus 2IB equals to 10 volts is what I'm left with. Distribute this out again. So I'm left with the 6IB minus 6IA plus the 2IB equals to 10 volts. And again, these two are together, so make it simplify it for me. And then we have here the 8IB, and you have minus 6IA, this is a positive, right, equals to 10 volts. And I finally have my second equation done. Okay, so again, what do we have here now is that we finally have here, this is our loop 2 equation, loop B equation. So we finally have two equations and two unknowns, which we can finally solve, right? So let's put them all together. You can see it together. And we also put a line here to separate everything for you. And then I'm going to put here, this one here. Okay, perfect. So now I have my equation 1, I have my equation 2, and I can finally solve. All right. So, you know, it's really up to you and how you want to solve, but let's solve it using both ways. The first way we're going to use is going to use our substitution method. I'm going to show you another technique. Then I'll go over this in one more time as far as giving you an overview of what to expect. So if we use a substitution technique, I have to now isolate one of my variables. So say if I wanted to solve for IA, then I'm going to left with 7A equals to minus 5V plus 6IB. This is from EQ1. And if I take, sorry, I'm going to add some more pages. So if I take here, in a couple pages. So if I take this EQ1 and I sub, so I'm not even finished simplifying, go one more step. So I'm going to have here IA equals to minus 5 volts plus 6IB all over 7. Okay, So I'm trying to simplify this. And so I take my one unknown from equation 1, and I'm going to sub into EQ2, into equation 2. Okay? So anywhere, any place I have an IA, I'm going to substitute it with this. So I'm going to now take equation 2, which has -6, and I have an IA term there. So I'm going to put here -5 volts plus 6 IB over 7, right? Plus 8 IB equals to 10 volts. Why am I doing this again? Is that because I'm trying to have, hopefully, one unknown so we can go ahead and solve, right? That's the math objective behind this entire thing. All right, so now that we have that, now we have to do some algebra on this to solve, right? So we have here negative times a negative gives me back a positive 30V, right? Then I have here minus 36 IB over 7 plus 8 IB equals to 10. So now we're going to try to simplify this as best as we can. So we're going to have here, so I'm going to probably left the fractions, which is not so fun for some of you, or I can leave in decimal place. So let's just round to, let's just go to 2 significant figures, not to go too wild for now. And then let's see what we get. Okay, so I'm just trying to simplify this, and what we're going to be left with is hopefully something that makes sense for all of us. Okay, so here is what I get when I simplify this. And move this over a little bit, just doing some hopefully basic algebra and trying not to make any algebraic mistakes, and we should be good to go. This is what I got when I do the algebra. And now if I solve for IB, I get back 2 amps. Okay, so that's if you're going back down to about 2. Well, you need at least 3 significant figures to make it perfect, of course, or more. But you should get about 2 amps when you do that. Okay, so once you get the 2 amps, it's fantastic. We can now take that value of the 2 amps and substitute it back in to either equation 1 or equation 2, and we're done with it, which is exciting. So let's see. Let's put it back into equation number 1. I'm going to copy that and place it over here. So if I substitute back in the value of 2 into this, I can solve for the current in the other loop. So this is what you're going to be left with, equals to -5 volts. So you're going to have here minus 12 volts equals to -5 volts and then 7 IA, right? So if I solve for IA, I'm going to add 12 to both sides. So I'm going to add 12 volts, and then I'm going to have here 7 IA. So what is that? So it gives me back, so it gives me back 7, right? So it gives me back positive 7 volts, 7 IA. So then IA, this is ohms, right? It brings us back to 1 amp. All right, so try that out. And just like that, we're done with the problem, which is exciting. So we got the currents there. And if we wanted to know the current through the middle branch, right? Well, we're ready to find that our constraint based on our loop equations, right, is the following. We can say that our constraint is this, and we copy and paste it. And what we anticipate, is that IA is 1 amp minus our IB, which is 2 amps, equals to IC. So we were expecting our value of IC to equals to minus 1 amp. Okay, and again, there's no technically positive or negative amps. Amps is nothing else, but then positive and negative is just referring to direction. So if we ever receive a value of negative amps, that means our assumed direction is just opposite of that. So we thought the flow of the current was going clockwise or downwards in this particular problem. What the minus sign is referring to is that our direction of our current is actually going upwards, right? It's actually going, we assumed it's going like this, but it's actually going up in this direction, okay? And that's what that means. And hopefully that kind of makes sense to us of what's going on. We could also do a couple of proofs on this to see if we're right as well. And I really enjoy the proofs on circuits because it really helps identify what in the world is going on, right? So the first proof that we are hopefully remembering from reading the book or just practicing or taking a look in a previous video is that when you have resistors in parallel, their voltages are all the same. If you have branches in a circuit that are in parallel, their voltages are all the same. So remember what we solved for. We have a value for IA to be 1 amp, right? So IA equals to 1 amp, and we have a value for IB to be 2 amps. Right? And then we know what we have minus 1 amps to be IC. Okay, let's see if we're correct. This is a quick check, I hope. So what we're going to do now is that I'm going to put the voltage, the current back into our circuit. So if I have here, I'm going to delete this just to be a little bit more clear. Because this is the left-hand side, that means that this is 1 ohm. That means that there's 1 amp going through here. Let me highlight that again so you hear it clearly. Right, so that loop has 1 amp. And again, the 6 ohms is very unique because it shares the current between both the IA and IB, but that's just an arbitrary value that we made up to help us solve these problems with this technique. So what we also know with certainty, we know that IB, we solved it to be 2 amps over here, okay? So if you multiply the 2 amps by the 2 ohms, you get back 4 volts, okay? If you multiply the 1 ohm by 1 amp, you get back 1 volt, right? So that means that there's 1 volt going through the resistor, right? And there's 4 volts. Say it more clearly. There's 1 volt going through the 1 ohm resistor, and the 2 ohm resistor on the right has 4 volts that it's actually going that you can measure through it. So what does that mean? So if I look at this variation, so we put this value, hopefully this is easy to copy and paste as well. Here it is. So I'm going to put this here because to me this is a lot more logical to look at here. I'm going to copy and paste this here just for clarification on how we're going to approach this. So when you approach this now, you have 3 branches, and on each branch, right, we expect the voltages to be the same. So how could that be? So let's put down the numbers here to see that more clearly. You can have 5 volts here, minus positive, and you're going to have 1 volt here, positive, negative. So in other words, to read the leftmost branch, it's the sum of the voltages. So if I start from the bottom, the ground side, sorry, I didn't mean to do that. You start from the ground side, you're going to read it as minus 5 volts plus 1 volt equals the left branch, I guess, just for lack of better terms, right? Normally I label them, but let's just go with that. So I get back a net voltage of minus 4 volts from the bottom. Now let's look at the far right branch. Well, remember we showed you before that we have negative positive 4 volts here. So equals to the right branch. You can see that we get back minus positive 4 volts if we're reading it from the bottom branch, That's interesting. So you put this over here so it's more legible. Move this here so it's not so disorganized. And then when we do equals the center branch, right? The center branch states that you have here a potential difference of minus 10 plus 10 volts. And then it was positive minus 6 times it by IC, which is 1 amp, which is what we solved for, which gives us back 6 volts here, right? So 6 volts is what we get back. So ultimately, what we get back in the middle is also 4 volts, which showcases us that we did the right thing. And if you're wondering the sign convention, maybe more clear, since I'm using the equation, let me put it this way, so it's made a little more obvious. So right now I'm using the constraint equation from the left loop. So in other words, what that means is that positive negative here, but because I have a negative 6 volts, it actually inverts the positive negative value back and makes it, instead of it being positive on the top, instead of it being positive on the top, negative on the bottom, this actually becomes positive on the bottom, negative on the top, because this is a minus 1 amp, so it inverts the direction flow. That makes sense. So in other words, what we expect again is that we will get back a total of minus 4 volts as well. So we prove that all the branches have the same voltage, which we should feel comfortable that the answer is definitely correct. Okay, that's a huge plus when you see that. Another thing that I wanted to add while we're here is that when you look at these problems, what's important is that you have here the KVL equation, right? So I talked about KVL and I did the sums of the ins equals to the sums of the outs, if I can find that. Okay, so ultimately this section over here is fundamentally important, because here, although I wrote it in this form, I could have also wrote it in the form that equals to 0. And how is that? Well, there's an equal sign on this equation, which means that I could also have written this by moving the IC, leaving it there, and moving the IB and the minus IA from the right-hand side of the equation to the left. And I'll be left with IC minus IB plus IA equals 0. So this is how Kirchoff's Kirchoff's current law also works. So I like to call it sums of the ins equals the sums of the outs, or it's KCL. It's the same thing. It's exactly the same thing algebraically as well, as you can hopefully detect it from what I just wrote. I just summed them all equals to 0, which is really important. And the same if you wrote it from the other loop's perspective as well. You could also end up with a sum equal to 0 too for the secondary loop, right? So I could also write this one in the classic KCL form, which is all of it equals to 0 by moving anything I want over from either everything from the left to the right or everything from the right to left, and they algebraically are the same. So I could also have written it as, let me give myself a little more space, IA minus IB minus IC equals to 0, and this is its classic KCL form, which is kind of cool as well, which means the sums of all the currents that are going in or out of that node are pretty useful too. So remember what I said before, there's also an easier way to think about it, because I like to not tax my brain if I don't have to. And one of those things that you can do when you're doing this problem, and I won't do the entire problem in its entirety all over again, but the idea will hopefully hold true for you, is that we can do the following. We can simply do this. Add a couple pages here. We can simply have not overthought it. So the only resistor that is shared between both currents, again, is a 6 ohms. So it looks like this, right? IA and IB. To save time and energy, since we already showed you the actual proof of where this comes from, you can simply just write the equation out. So like this. So what you can think about this as a train, right? So you are on a train. Your train is called IA, and the resistor, you can think of it as a platform at a train station, right? Oh man, this looks not neat, but I'll try to write it one more time here. You know what? I'm just going to delete it and try one more time, since I'm being a little more specific. So here, again, here's our resistor, and that's our constraint resistor because it's shared among two different current sources. So because it's shared, think of it like this. Think of it that you are physically on a train, and that train is called IA. And here, I'll even add a little bit more to it so it looks like an actual train. And this here is the actual platform. If you thought about it this way, and here is IB, right? And that's another train. So when you do this and you just write your mesh equation, right, for left loop or mesh loop A, the only thing you gotta do is just think about it as if you are on a train, IA. How does IB look like to you? Well, it looks like IA is going across IB, and that's it. Don't overthink anything. So let me explain to you what I mean about it again. You will simply just do minus 5 amps, sorry, minus 5 volts, like I said before, plus 1 times it by IA, and then don't think I do is plus 6, and don't overanalyze it. Say if I'm analyzing loop A, then I am physically in this side of the train, right? The left of this train. It's going to appear to me that my train called IA is going opposed IB plus 10 volts equals 0. No thinking involved. And now if I did the problem from mesh B's perspective, let me call it mesh, sorry, gotta think of a name, loop B's perspective, right? Then I rethink about, I don't have to overanalyze again at all. Here I copy and paste this. And this time, I'm going to delete this side. Sorry, delete please. Good. So now if I highlight this side, so now I'm a passenger. I'm a passenger now. No longer in train B. Why? I'm over here, right? And I'm also analyzing loop B, which means I'm on the loop B side of the world. It appears simply that loop B is going positive clockwise direction and everything else is going opposite. So I'll quickly do the equation again. Be minus 10 volts if I start from the bottom, plus, it's always going to be plus if you think about it simply, it's always going to be 6IB minus IA. That's it. Don't overanalyze anything. This is how you can perceive these problems. Plus 2IB equals 0, and you're done with it, right? I showed you the other way before just so you can get an in-depth understanding of where all this comes from, but to be honest, I like to think about it without overburdening my brain as that if I'm analyzing loop A, I'm imagining that I'm on a train that's going positive clockwise direction. Anything else is going opposite, is just minus for me. So I get a minus IB. If I'm evaluating loop B, then I'm physically on a train called IB, then IA looks like it's going opposite my direction. And it's as simple as that. I'm not overtaxing myself or over worrying about anything else. It's really that simple as far as thinking about it, but that comes with experience. The other technique that I showed you earlier comes very handy when we work on something else called dependent sources or larger circuits or more complicated circuits. You're going to need that technique in your back pocket to help you solve for that. But overall, you don't need. Other thing I want to recommend, that to solve these problems faster, instead of using the substitution method using math, I would recommend using a matrix. Matrices. It's really hopefully easy. You're going to just create a determinant that's 2 by 2. You can call it A1, A2, B1, B2, and you can solve for your determinants by doing exactly what I have here. You'll just do A times D minus B times C. Some techniques you learn hopefully in your math class. Determinants again. You can write it in either this form or this form. They're the same. And here how it looks like mathematically. It's another form also called Cramer's rule. A1 times it by B2, and then minus A2 minus B1. Right. This is the method that I recommend that you use for circuits or mostly math classes. It's going to come in handy, or any of the engineering classes. This is certainly one of the more important techniques to use. And then once you have that, right, say if you have an example of A1 plus B1y equals to C1, A2 times X plus B2y equals to C2, you can now solve for your unknown variables X and Y. And if it's not clicking yet, instead of this being x and y, it'll be IA and IB from our previous example that we just worked on. So take a look at this. You can always pause the video here, but I like to look at examples because it helps me understand things a lot more simple. But say if you had a problem where I asked you to solve 4x minus 3y equals to minus 14 and 3x minus 5y equals to minus 5, how would you solve this, right? And thankfully, the determinant is really straightforward and easy. What you would do is that you would create a matrix from our values of the 4, 3, minus 3, minus 5. So I get 4, 3, minus 3, minus 5. And then I would solve for that, right? And that gives us our capital D. In other words, I'm going to do 4 times it by minus 5, right? Minus 3 times it by minus 3. So how I like to do it in my notes, at least in my head, is I'm doing this. Right? I'm doing this two together. So I'm ending up with minus 20 minus 9 is what I'm left with. So I get my determinant to be equals to minus 11. So say if I wanted to solve for this value of x, right, this value of x over here, which is for both equations, to solve for x, it's going to be c1 over times c2, b1, b2, and etc. as you see here as well, or just call it c1, c2, b1, b2 over big D. And don't forget what c1, c2 is. Well, I showed it to you over here. c1 is the solution to your two equations to a known problem. So in my case, it'll be the minus 14 and minus 5 for this example. So what you would do then is that you'll now, where you have the c1 and c2, you replace it with minus 14 and minus 5, and you'll leave the b1 and b2 in their place, which is minus 3, minus 5. You take the minus 14, you'll multiply it by the minus 5. You subtract it from the minus 5, and then the minus 5 times it by minus 3. So I'm doing basically cross multiplication like this. Okay? And you're left with a value of 55. Okay? And then your final answer for x is going to be 55 divided by minus 11 gives me my solution for x. So x equals to minus 5. So in this particular problem, I can put in x equals to minus 5, right? And I'll repeat that again. If I want to solve for y, I'll do the same. It'll be a1 times over a2, a1, a2, c1, c2 is my matrix. So in this, for this particular problem, it's going to be 4 times it by minus 5, minus 3 times it by minus 14. So I'm left with minus 20 minus 42. And get back a positive 22. So when I solve for y, I'm left with a value of negative 2 back. So for a challenge for you guys, I'd recommend that you retry the problem that I just worked on right now, but this time use determinants using matrix and just literally plug and play, and you should get back the same answer we had before, which was the minus 1 for IC, 1 and 2 amps to be the solution. All right, that's an introduction to our mesh. I will plan to put out several more problems to get the hang of it. I'll do several more 2x2 matrix type problems. Then I'll do 3x3 as well to get the hang of it. And hopefully after that, this will actually feel much better. Hopefully you learned something. Please make sure you like this if you liked it, and I'll see you next time.